We introduce Inpaint4Drag, a novel framework that repurposes existing inpainting models for drag-based image editing through our bidirectional warping. Our method enables intuitive drag editing capabilities without requiring specialized training, making the powerful drag-based image manipulation more accessible. First, let's introduce what drag editing is. It's an intuitive image editing method where users can change the size, shape, and position of image content through simple mouse clicks. For example, in this scenic image, a user can click on handle points at the mountain peaks and drag them down to target points at lower positions, effectively reducing the mountain's height. This direct manipulation approach makes complex image transformations as simple as dragging elements to where the user wants them to be. Here are some more examples to showcase the versatility of drag editing. We can make this adorable kitten wink by simply dragging its eyelid closed, creating a charming expression. For landscape editing, we can reshape coastlines by dragging the beach boundaries to create different coastal formations. With sculptures, we can rotate this classical bust's head by dragging it to a new orientation, giving it a completely different perspective. These examples demonstrate how drag editing works across diverse image types, from cute animals to natural landscapes to artistic sculptures. Now let's briefly review existing drag editing methods. The majority of previous approaches are built upon stable diffusion, so let me walk you through their typical pipeline. First, the input image is encoded into latent space through VAE's encoder, where the image undergoes 8 times spatial compression. Next comes the inversion process. This is where we reverse the diffusion process to find the initial noise that would generate our input image. Starting from this noise, the methods then perform denoising to reconstruct the image. To achieve the drag editing effect, that is, moving content from handle points to target points, existing methods typically use 2 main strategies. The first approach extracts features from handle point locations during the inversion stage and pastes them to target point locations during denoising. The second approach extracts features from both handle and target points in the UNet feature maps across both stages, then computes a loss to optimize the latent representation. These interventions are applied at specific denoising steps or across multiple steps. Finally, after denoising is complete, the VAE decoder generates the final edited image. However, previous methods have several key limitations. Let me start with the first major issue, which is imprecise control. When users specify handle and target points, they do so in the original image space at full resolution. But previous methods perform all their operations in significantly downscaled spaces, either in VAE latent space with 8 times downscaling, or in UNet feature maps with even greater 16 times or more downscaling. This creates an inherent precision bottleneck, where precise user inputs are lost due to spatial downscaling. Let's look at some concrete examples of this imprecise control limitation. Here we have 2 seemingly simple editing tasks: making a cat close its eyes and elongating an earring. Intuitively, these should be straightforward edits requiring only minor local modifications. However, as you can see, all existing methods fail to achieve these precise edits. This failure stems directly from their reliance on latent space operations, where spatial downscaling prevents fine-grained control. The second major limitation is their limited capability for large occlusions. Previous methods rely on general-purpose text-to-image models that aren't specifically trained to handle missing or occluded regions. Here we can see 2 examples that demonstrate this weakness. In the first case, we want to move the camera to reveal the person's face that's currently hidden behind it. In the second example, we're trying to open the lion's mouth to show its teeth and inner mouth area. As you can see, all existing methods struggle with these scenarios because they lack the specialized capability to generate plausible content in heavily occluded regions. The third major limitation is input ambiguity. A single drag operation can be interpreted in multiple ways, leading to unpredictable results. For example, here we have a polar bear with a control point on its paw that we want to drag upward. This simple drag input is actually highly ambiguous. It could mean we want to translate the entire bear, bend the forearm, raise the hand, stretch the upper body, or even translate the entire scene. This demonstrates a fundamental issue with previous task settings. the same user input has multiple valid solutions, which means the model's output often fails to align with the user's true intention. To address these three limitations, we propose a novel solution that decomposes drag-based editing into two steps. Users first specify the regions they want to deform, then use control points to guide the transformation. Our bidirectional warping algorithm is real-time, providing immediate preview and eliminating trial and error cycles. By computing dense motion for every pixel, we avoid ambiguity issues from sparse control. We demonstrate the two major steps of our approach as follows. Step 1. Pixel space bidirectional warping. Here we see a bird in flight, where the user has marked the left wing as the deformable region and uses control points to guide its transformation, achieving precise geometric changes. Now let's move to step 2, which is image inpainting. After the bidirectional warping step, we have successfully deformed the bird's left wing as desired. However, this geometric transformation creates gaps or holes in the image where content is missing. This is where our image inpainting component comes in to fill these missing regions with plausible content, ensuring the final result looks natural and seamless. The inpainting step is crucial for handling the occlusion challenges we discussed earlier. Unlike general text-to-image models, specialized inpainting models are specifically designed to handle large occluded areas more effectively. Now we show our demo interface in action. This is our interactive editing tool called Inpaint4Drag. After users upload an image, the editing process follows our two-step approach. First, in the Draw Regions step, users select the deformable regions they want to modify, shown here in red on the paintbrush. This gives users precise control over which parts of the image will be affected by the transformation. Next, in the Control Points step, users place handle points, shown in red, and drag them to target points, shown in blue. In this example, we're adjusting the angle and position of the paintbrush. Notice how intuitive this is. You simply drag from where the feature currently is to where you want it to be. Our system provides real-time preview, so users can immediately see the warping results and make adjustments if needed. Once satisfied with the deformation, clicking Inpaint triggers our specialized inpainting model to fill any gaps or missing regions created by the geometric transformation. To help users achieve precise object boundary selection, we integrate SAM, the Segment Anything model, for intelligent boundary refinement. Our method uses SAM to automatically detect precise object boundaries from rough user masks, then constrains SAM's output using eroded and dilated versions of the user's rough mask to preserve user intent. As shown in the chess example, the user draws a rough circular mask around the red chess piece. SAM predicts more precise boundaries, and our refinement process uses morphological operations to constrain the result within the user's intended region, producing a clean, accurate mask that follows the exact contours of the piece. Now let's dive into the core of our method, step 1, which is bidirectional warping. Our algorithm deforms masked regions precisely according to user-specified control points. The key strength is computing dense motion fields for every pixel, ensuring smooth transformations. By providing complete motion guidance rather than sparse control, we eliminate deformation ambiguity. Let's now walk through our algorithm step by step. Starting with the inputs to our method, we have an image, a user-defined mask highlighting the region to be deformed, and control points that specify the desired transformation. Given the user inputs, our target is to estimate a dense motion field that enables seamless appearance transfer by directly copying and pasting pixels to their computed target locations. When we have only one pair of control points, we can apply the same displacement to the entire region. This is the simplest case. With a single control point pair, every pixel in the masked region undergoes the same translation. The entire object moves uniformly according to the displacement vector defined by the control points. However, when we have multiple pairs of control points, unidirectional mapping through interpolation leads to holes and gaps. As shown in this example, when we try to deform a region using multiple control points by interpolating and forward warping each pixel, the resulting transformation creates visual artifacts. Some areas in the target region may not receive any pixel information, leading to holes and gaps in the final result. Therefore, we need a method to handle these holes and gaps. Our approach works in two steps. First, we forward warp the contours of the source region to determine the exact shape and boundaries of the target region. This ensures we know precisely which areas need to be filled. Then, instead of forward warping pixels which can create gaps, we use backward warping. For each pixel in the target region, we trace back to find which pixel in the source region should provide its color value. This backward extraction guarantees that every pixel in the target region receives appropriate content, eliminating holes and gaps. So far, we have deformed the image content using the masking control points, leaving vacant areas that need to be filled for inpainting. We've successfully applied the user-specified deformation, but this creates empty regions where the original content was moved from. These vacant areas need to be filled with plausible content through inpainting to achieve a natural-looking result. The second and the final step in our pipeline is to apply an inpainting model to generate content for areas revealed during deformation. For implementation, we use Stable Diffusion version 1.5 Inpainting. We've incorporated several efficiency optimizations including Tiny Autoencoder, LCM LoRa for reduced sampling steps, and prompt embedding caching to ensure responsive real-time performance during editing sessions. A key advantage of our approach is its compatibility with different inpainting models. As shown in these examples, we can seamlessly integrate various inpainting methods including Deep Fill version 2, Llama, and different Stable Diffusion inpainting models simply by providing them with our warped preview image and inpainting mask. While our implementation is based on Stable Diffusion, this modularity ensures that as better inpainting models emerge in the future, they can be directly incorporated into our drag editing framework without any modifications. Thanks to our decomposed approach, we achieve extremely fast preview generation in just 10 milliseconds, plus about 1/3 of a second for inpainting. This represents a 14 times speedup compared to the second fastest method, enabling truly real-time interactive drag editing. Our quantitative evaluation demonstrates significant advantages across multiple metrics. Beyond the speed improvements we just showed, we maintain competitive editing precision as measured by MD scores, which indicate how accurately we follow user drag instructions. Our LPIPS values also show that we effectively preserve image identity before and after editing, ensuring high-quality results. Here we show quantitative results comparing our method against state-of-the-art approaches. As you can see, our method significantly outperforms existing methods across challenging test cases. The key advantages are clear. We generate realistic content in previously occluded regions, like newly exposed facial features and the lion's open mouth. Our pixel space approach enables accurate manipulation of local details that latent space methods miss due to downscaling. In conclusion, Inpaint4Drag addresses the fundamental limitations of existing drag editing methods through our novel bidirectional warping approach. Our decomposed two-step pipeline combining pixel space warping with specialized inpainting delivers precise control, handles large occlusions effectively, and eliminates input ambiguity. Key contributions include millisecond-level preview generation with 14x speedup, competitive editing precision while preserving image identity, and compatibility with various inpainting models. Our method enables accessible drag-based editing without specialized training. The real-time preview transforms editing from trial and error to intuitive, immediate feedback. Thank you for watching, and we look forward to your feedback and questions about our ICCV2025 paper.